Universidad Nacional de Colombia, proyecto cultural, científico y colectivo de Nación.
Buenos días a todo el mundo en Colombia. Good morning, everybody. It's a pleasure to me as a faculty member of the Universidad Nacional de Colombia and the leader of the Colombia Untitled Chapter to present you the Kimberly-Clark Distinguished Lecture. This year we have we have Professor Dr. Mohamed Sahimi from University of Southern California in Los Angeles, who's giving a talk titled Porous Media, Small and Large, from Atomistic Modeling of Nanoporous Membranes to Modeling of Flow and Transport in Geological Formations. Professor Mohamed is Professor of Chemical Engineering and Material Science and the NIOC Chair in Petroleum Engineering at the University of Southern California in LA. He received his Bachelor of Science degree from University of Tehran in Iran in 1977, the year I was born. His PhD from the University of Minnesota in 1984, both in chemical engineering. He joined to University of Southern California in 1984 and was the chair of his department from 1990 to 2005. His research interests include flow, transport, reaction, adsorption, deformation in porous media, characterization of fracture networks of rock, transport of fluid mixtures in membranes, and transport of fluids and macromolecules in nanostructured materials. He was published over 400 papers and 4 books, and has received several teaching and research awards, including the Interpor's Honorary Member Award for Lifetime Achievements. So it's a pleasure to us in our anniversary of our university. We are celebrating 160 years of teaching engineering in Colombia. Thank you very much, Mohamed, for your talk. And now we are ready to see your presentation.
Good morning, everybody. I'm happy and honored to be speaking to you from Los Angeles. I wish I could be actually there, but because of the COVID situation and lots of other things, it was not possible. I have
Sorry, Mohamed. Could you start your camera?
I thought you already see the picture. You don't see the presentation?
Yes, but okay. But we don't see your camera. Maybe.
You mean you want to see me or you want to see the presentation?
Okay. What the thing that you prefer is good for us.
Do you see the presentation?
Yes.
Okay.
But now in the same menu, but in the bottom you can choose. You can start your camera.
Let's see. Okay. All right.
Good. It's good to see you.
Okay. So you can see the presentation.
Yes.
Okay.
Yes, we have.
All right. Okay, so I'm very happy to be here. As I said, I have actually several friends that are originally from Colombia, including Professor Hans Hermann, who is very well known in physics and applied physics, and received an award a couple of years ago, a very important award. Today I'm going to talk about something that relates to geological formation, which is part of what I talked about at the Interpol. And that is characterization and modeling and upscaling of larger scale porous media and modeling of fluid flow in such formation. And what I'm going to describe to you is how we use two relatively new transformation, namely wavelet and Kerber transformation, to do this. Of course, we all know that anybody who has worked on porous media knows that porous media, especially the natural ones, rock, for example, soil, and so on, are very complex, and characterization and modeling of that is very difficult and fraught with difficulties. The reason for it is that there are many relevant length scales that must be taken into account. Let's say porous scale, core scale, and larger. And the difference between these length scale is very large. Pores are very tiny. Cores are on the order of, let's say, a few centimeters or a foot or something. And then when you go to field scale, of course, it's very large. And then even after field scale, we have regional scale, which is even larger. At field scale, of course, the data are very limited because it's difficult to collect data at field scale. For example, in oil reservoirs, you have to drill wells and collect samples, and therefore, since these are expensive, the amount of data are limited. In addition, because the data are limited, there is also large uncertainty in whatever interpretation that we make from the limited data. So in order to take into account all the relevant factors, we need to develop a very high resolution model, which can take every relevant information into account. And then that high resolution model is usually something that is very difficult to actually simulate because it contains millions of grid blocks. And if you want to do, for example, simulation of two-phase flow in such a high-resolution grid and simulate it under unsteady state condition for, let's say, a year or two, make predictions for a year or two, then that becomes very difficult. So that also means that we have to develop efficient computational strategies in order not only upscale the model so that we make it manageable, but also do the computation as efficiently as we can. And of course, this is not a new problem. Petroleum chemical engineers have worked on it, civil engineers have worked on it, groundwater people have worked on it, and therefore many approaches, algorithms, strategies, and so on have been developed. It's not, the problem itself is not new. What we're trying to do is to develop a new approach to it. And that is what I'm going to talk about. I'm going to describe a method based on multi-resolution wavelets and Kerber transformations. So let's first define what a wavelet transformation is. Basically, a wavelet transformation is when we have a bunch of data, whether it is in terms of time or in terms of the space. We decompose the data into a set of functions, which are called wavelet basis functions. And this can be done at different length scale, or if the data is time dependent, at different time scale. The way we define it looks like this. Let's say that you have a data f of x, which could be where x could be time or space. And then we define it as the integral that you see, f of x times psi of a and b dx. Psi of a and b is related to a function psi, which is defined by the equation that you see on the screen. In this equation, as you can see, b is like a window, because if you change b, the position of the function changes. A is like a like a macroscope. You can increase it or decrease it, and therefore you can stare at finer and finer scale, or you can stare at it at coarser and coarser scale. Psi is called the mother wavelet, and as you can see, by changing the two constants A and B, you change the function that you want. The definition of wavelet transformation, as you can see, is very much similar to, let's say, Fourier transformation, except that the kernel in Fourier transformation is the same, is e to the I omega x, but here you can choose what kernel you want to use, what psi of A and B you want to use, depending on what application you have in mind, and therefore you have great flexibility in it. There are many types of wavelets that have been developed. As I said, it depends on what application you have. One, for example, very well known is Riker or Mar, or sometimes people call it the Mexican hat, which is given by an equations like this. So it's basically like basically it's like a Hermite function. And it has been used in signal processing, cosmic microwave background radiation analysis, and so on. The reason they call it Mexican hat is because it looks like this. When you plot it, it looks like this, which is a very nice, sort of nice Mexican hat. So that's why they call it Mexican hat wavelet. But the most famous one are the Derbyshire wavelets that were developed by Ingrid Derbyshire, who was a professor of mathematics at Princeton University, and I believe she's now at Duke University. There's a whole family of these Derbyshire wavelets from dB2, dB1, and dB2, all the way to dB10. You can see as you increase the order of wavelet, the details changes. The dB2 is also called the Haar wavelet, which is the simplest that you can use. This is, of course, in one dimension, but you can generalize it in 2 dimension and 3 dimension. In fact, that's what we have done. Now, one of the advantages of these wavelets is that they have compact support. What it means is that they are non-zero over only a finite interval and zero everywhere else. So that, first of all, facilitates efficient computation. Secondly, if you remember, we had a window size B in the definition of wavelet. So by changing that, we can change the position where the wavelet is non-zero and where the wavelet is zero. So again, that offers you great flexibility. Wavelets can represent or decompose smooth functions, as well as those that have discontinuities. As I said, you can zoom in and zoom out. You can detect sharp spikes, and I'll show you in a few minutes, and discontinuity at different resolution using wavelets. And you can construct it. You have great flexibility in terms of constructing it, so that any property that you wish to have, it can have it, such as orthonormality and so on. Then we have wavelet coefficient. Wavelet coefficients, which is basically those wavelet transformation. We have 2 types of wavelet coefficient. One is a scale coefficient. One is detail coefficient. A scale coefficient of a data series, wavelet scale coefficient, contains information at a fixed scale. In other words, all the information that you have, let's say, in a block of a computational grid block, is contained in this scale coefficient. The detail coefficient, on the other hand, contains information about contrast between data at 2 different scales. So let's say in a computational grid, you have some small blocks and some large blocks. So obviously there are certain differences between the content of the 2 blocks, and detail coefficient actually has information about those, which we use in our computation. So a scale coefficient, for example, in 2 dimension, S is defined by the top row, and you can see it. Then we have 3 detail coefficient, You can see they have superscript 1, 2, and 3. 1 corresponds, let's say, to the x direction, 2 corresponds to the y direction, and 3 corresponds to the diagonal direction. So that means that you can collect information in different directions. Okay, and the index n is a scale or level. Phi is the scale function. K and n are discrete grid points in the computational grid, and psi is the wavelet that I mentioned to you. The two functions, phi and psi, are actually related. So knowing psi, you build phi. So the two are related. Now, how do we use this for porous media problem? We have used it for analysis of data. We have used it for pressure transit analysis. Other people have also used it for pressure transit analysis. We have used it for numerical simulation of transport flow equation. We have used it for determining fracture densities at various parts of the, let's say, an oil reservoir. And we have also used it for upscaling, which means that you will start from a very high resolution, large computational grid, and then you make it coarsened, you upscale it, so that you will use the number of computational block in your model, so that the computation become manageable. But at the same time, you do it in such a way that you don't lose any important information by upscaling. Okay, so let's for example look at analysis of well logs. Of course, well logs people have shown for many years that they contain long-range correlations. These long-range correlations are represented by a self-affine stochastic function, such as FBM, fractional Brownian motion, or FGN, fractional Gaussian noise, and both of them are characterized by an exponent which is called the Hertz exponent. The Hertz exponent basically characterizes the type of long-range correlations that we have. Hertz exponent is typically between 0 and 1. If Hertz exponent is between 0.5 and 1, the correlations are positive, which means large values are followed by large values, low values are followed by low values. Hertz exponent between 0.5 and 0 characterizes negative correlation, which means large values are followed by low values, and so on. So Hertz exponent between 0 and 0.5 represents a very heterogeneous system, whereas Hertz exponent between 0.5 and 1 characterizes a relatively smooth system. And the data that contain this type of correlation can be analyzed by a variety of methods, in fact. And many years ago, we actually published a paper in which we compared various methods that you can analyze it in order to answer the following questions. What is the most accurate method of estimating H? Because if you estimate H, then you can generate realizations of the data. And what is the fastest method? More importantly, because the data are limited, the more important question is, what method needs the least number of data points in order to provide an accurate estimate of the Hertz exponent, by which you generate synthetic data that follow the statistics of your data. So the way we do it with wavelet is we calculate the wavelet detail coefficient, the way I defined it for you. N is the size of the data, so you have, let's say, 10 data points or 1,000 data points. And J is an integer, and K is 1, 2, 3, and so on. So f of x is your data. So we fix J, we vary K, and compute djk. So for every J, we have n of these because we have n data, and then we compute the variance of these n coefficients that we calculate, and then we can show that if you plot log of this variance that you compute based on wavelet detail coefficient, the slope is 2h plus 1 times j plus a constant, which means that if you calculate the slope, you get the Hertz exponent. This was a paper that I mentioned a long time ago. We published a long time ago, in which we compared various methods for analyzing this type of data, and all the details are in that paper. Now, what are the advantages of this? Well, the advantage of, as I said, this, such data can be analyzed by many methods. So this is not just analyzing it is not very new or novel, but it has advantages. The advantage of that, first of all, the method is very fast, and also is very accurate. And more importantly, as I emphasized earlier, is that even a small number of data points gives you good accuracy for the large scale structure of the data. Now, I'm sure at least some of you are familiar with the fact that these data can also be, excuse me, can also be analyzed by a spectral method. You calculate the Fourier transform of the variance and so on. But if you look at the Fourier transform, the power spectrum of the data, often these power spectrums are extremely noisy. So it becomes a matter of taste how you analyze these, because it's very noisy. But wavelet methods, because they have compact support and therefore are localized, they are far less affected by noise. And in fact, there is very little effect of noise in the system. So just to show you an example of it, on top you can see a porosity log from an carbon and oil reservoir in Iran. And at the bottom, you can see that variance that I told you versus J. And as you can see, you get a very nice straight line, and you get a slope of this. So it's very easy in this way to make sense of the data at the top. And not only that, but also because you estimated the Hertz exponent for this type of data, you can generate many realizations of the same data that follow the same statistics but differ in details. More importantly is the following. If your data show a crossover, that means that at a smaller scale they have one type of behavior, at larger scale they have another type of behavior. This type of analysis clearly show that. So in this plot, if you see, J is basically a space value. So as you can see, at smaller scales, they follow one straight line, and at larger scale, they follow another straight line. So that means at a smaller scale, you have one type of correlations, but at larger scale, you may have another type of correlation. So there's a crossover between the two, and methods like spectral methods cannot really find this because, first of all, the data, the power spectrum is very noisy, and because it is noisy, it would be very difficult to distinguish different scales in that type of plot. We can also calculate cross correlation, which is important, but hasn't been paid attention as much as it should. So, for example, we have gamma ray, we have sonic transient time, we have neutron porosity, and we have bulk density. So these are four actual logs from an oil reservoir in southern Iran. And we want to know whether there is cross correlations between the two. In other words, between any of these two. In other words, we want to know if we have some insight, for example, about the gamma ray log. From that insight, can we get any insight into bulk density and neutron porosity? And in order to do that, we do cross correlation. And in order to do cross correlation, we do cross wavelet transform. So let's say we have two logs or two series. One is X, one is Y. And then we construct dxy as a product of dx for series X and dy for series Y. A star that you see on top of dy is compressed conjugate. And then you define a coherence wavelet coherence coefficient, which is defined by that. S is a smoothing function, that smooths the data a bit. And then there's also a phase difference between the imaginary and the real part. So I is the imaginary part, R is the real part, and we define these two. And then if phase difference is between 0 and 90 degrees, then we say that the two series X and Y are in phase, but Y leads X. In other words, large fluctuation in Y are followed by large fluctuations in X. On the other hand, if phase difference is in between 90 degrees, 100 degrees, then it is X that leads Y. In other words, if you stare at X and see large fluctuation or a small fluctuation, then without even looking at Y, you can say that Y follows the same type of pattern. If it is 0, then that means they move together, they have perfect harmony between the two. And if it's 180, then we say it's antiphase between the two. Okay. So for example, here we have gamma ray and neutron porosity. The red contours indicate boundaries with high coefficients, with coherence coefficients. And the coherency ranges between dark blue, which is close to 0, and light green, which is close to 1. So you can see there are certain areas where there are cross correlations between gamma ray and neutron porosity, and in some other areas less. At the bottom you see gamma ray and sonic transit time, and you see the same type of difference. Here you see gamma ray and bulk density. Again, you see the same type of behavior. And we published the result of this in 2 papers back in 2011, one in physical and one in transport impulse. Then another question that we addressed using wavelet transformation was the Archie exponent. As you know, formation factor is related to porosity through a power law, which is often called Archie's law, and M is the Archie exponent. Now, the question that we addressed was M has been found to be to vary over a relatively broad range. In other words, M is not universal. It's not the same for all formations, and it can't be the same for all formations. And the reason hasn't been really clear how M varies, over a relatively large, and why it varies. And of course, because it's an important problem, and because Archie's law is used in practical simulation, is important to understand why M varies. So one of the things that we did was our analysis of well logs indicated that these well logs have multifractal properties. What it means is that if you take a piece of it, each piece is characterized by some sort of exponent which is not necessarily the same as other pieces. And we know that when we have long-range correlations and multifractal properties based on analogy with critical phenomena, the exponents that characterize these are not universal, they're not unique. They vary continuously, and they depend on Hurst exponent. So if you calculate Hurst exponent, you find that these exponents actually vary with this. And this is what we showed in 2 papers back in 2000 and 2001. So if the well logs are multifractal properties, the multifactorial properties, of course, is because of the depositional environment, because over thousands and hundreds of thousands or even millions of years, all sorts of things have happened in the rock formation, and the environment where things deposit, react, absorb, and so on have changed. And the reason that we see these multifactorial spectrum, which means every piece has its own characteristic, is because of the different depositional environment. That different depositional environment means that the Hurst exponent changes. And if the Archie exponent is a function of Hertz exponent, so that means that Archie exponent should also vary with the type of deformation. We demonstrated this by analyzing 36 resistivity log from 3 different types of oil reservoirs. So once again here, Wavelet transformation provided us with a very rational explanation. And the explanation for Archie exponent, that the depositional environment varies and changes. This depositional environment gives rise to various Hertz exponent. Because there are long-range correlations, this Archie exponent is a function of h, the Hertz exponent, and because h varies, so also does the Archie exponent. And we published this in a paper in Geophysical Research Letter back in 2015. We can also remove noise from data because we know, for example, natural data, well logs, for example, have a lot of noise. So the question is, how do we remove the noise without actually damaging the actual data? In other words, the actual data contains information, but if you remove the noise and during removal of the noise, you also remove some of the true information, then obviously you have hurt the data. So what we do is we calculate those Wavelet detail coefficient, and then we normalize all of them by the largest value. So let's say you have 10,000 Wavelet detail coefficient, you find the largest one, you divide every one of them by the largest one. So that means all the coefficients would be between 0 and 1. Then you set a threshold between 0 and 1. You say all the detail coefficients that are less than the threshold, I set them to be 0, and all those that are larger, I keep. Then you set a whole bunch of them to be 0, and then once you did that, then you can reconstruct the data. That means you calculate the inverse Wavelet transformation, going back to the real space. And I'll show you a simple example here. Let's say, for example, on top on the left, you have a signal or a noisy data like that. If I set, for example, a threshold at 50%, then I get what you see on the right at top. If I put it at 90%, then what you get is what you see at the bottom on the left. And if I put it at 95%, then you see what you see on the screen at the bottom on the right. Look at the one at the bottom at the right and compare it with the original signal on top on the left. You can see they are practically identical. All the structure of the data has been preserved, except that in the third level denoising with 95 threshold of 95%. That means I have set to 0 95% of the Wavelet detail coefficient, and yet it has preserved perfectly the structure of the data. So that again goes to show the power of this Wavelet transformation. Again, this is because of the fact that they have compact support. So as we look at different windows, we don't try to distort other parts of the data. We only zoom in a small region and try to remove noise in that small region or window. We can also determine fracture density along wells, for example. Of course, this can be done by sonic transient time, but a lot of older wells, for example, don't have such logs, and they're also expensive to run. But what we show is that with a well log as simple as porosity, we can actually detect fractures that cross the path of the wells, and that also helps, of course, in order to set up a model for an oil reservoir, for example. In order to do that, we take advantage of Wavelet detail coefficients or Wavelet transformation. They have a few very key attributes or properties. First of all, the Wavelet detail coefficient can be large even if the numerical value of the data at a given point is small. So what it means is that each piece of data is given its proper weight. The quantitative value of something may be small, but it has high significance. Secondly, local maximum in the spectrum of the wavelet detail coefficients provides clue about the scale at which these features are important. This is, I already mentioned. You zoom in and you look at that part. So, and also if data are composed of distinct types. So let's say you have for example, time series, or you have a well logs, and the well runs through several layers, for example. And each layer may have its own property because of the depositional environment. Then your well log composed of several distinct types, and wavelet detail coefficients actually indicate these differences when you plot them. And the power spectrum, the problem with power spectrum of the data that people often use is that power spectrum is a global type of measure, whereas wavelet detail coefficients are influenced by local structure because, as I said, they have compact support, and that's why they provide much better information. Now, to show you what I mean by this, let's look at this. On the top left, I show you a porosity distribution. Okay, now, all of them is just one distribution. Then on the right, I show you the same distribution, but I have changed 5 points in this distribution and replaced them by 5 other numbers. But you don't see them because the points that I have replaced with are very close to the porosity logs that I originally had. Now, if I take the wavelet transformation of the left, then I get what I see at the bottom on the left. You don't see any special features. It's basically a straight line with some fluctuation around. But if I take the wavelet transformation of the distribution on the right, in which I have replaced 5 points with some other numbers, then suddenly I see spikes exactly at the point where I had replaced those numbers. So even though those numbers had the same magnitude as the numbers that they replaced, but because their type was different, in other words, let's say, for example, I chose them from a uniform distribution between 0 and 1 or between 0 and 100, okay? And that distribution was different from the distribution that describe this. Remember, the distribution that's described is like fractional Brownian motion or fractional Gaussian noise. So if I replace them, then suddenly I see these spikes. So what does that mean? That means that if I have, for example, a well log that runs through the formation, and in its path it intersects, for example, fractures. Okay, since the fracture properties are distinct from the matrix properties, then I should see those discontinuity due to the fracture in the wavelet transformation of the porosity log. So, and the key to this, as I explained, is that these discontinuities cannot be seen by naked eyes, but they can be detected by wavelet transformation. We published this long time ago in Geophysical Research Letters. Here, for example, I'll show you a porosity log, and on top, I show you the corresponding permeability, and you can see where I have where I calculate the wavelet transformation of the porosity log. Then I see these spikes, and these spikes correspond to where I have a fracture. And they nicely correspond to permeability. For example, you can see on the right, you have a big spike in the wavelet, and on the permeability, you can see the same thing. Or on the left, you see a big spike in the permeability. You also see the same type of thing in the wavelet transformation of the porosity log. Even though the porosity log itself doesn't show any particular characteristic. For example, between 7600 and 7800, you see a big spike in the porosity, whereas the corresponding wavelet transform the permeability doesn't show a big spike. So it means that that large porosity is not really due to a fracture, but something else. People have also used it for water saturation and gamma ray logs, and they have found nice correlations between the two. Now, the other advantage of wavelet transformation is that if you have two layers, it doesn't confuse it with discontinuity. So let's say that you have a layered structure, two-dimensional model of a formation with layered structure, and you capture this wavelet transformation. At the top, you see the model itself, and at the bottom, you see the wavelet transformation of the same thing. And even though you see distinct layers in this model at the top, you don't see any special features due to those distinct layers at the bottom. However, if I displace the model, in other words, if I move two portions of it with respect to each other a little bit, so that I would generate the model at the top, then suddenly I see these distinct features that I have created in the wavelet space. In other words, for example, if you have a true fault or a true fracture, and you have data for that region that contains fault and fracture, but you don't see it particularly in the data itself, wavelet transformation of that data easily shows you where this fault or fracture may be. All right, so the next problem that we solved was upscaling of high-resolution geological model. And in order to do that, we use wavelet transformation. Geological models are those high-resolution models that I mentioned at the beginning. You generate a very high-resolution computational grid that typically may have, let's say, 2 million grid blocks. And you do it high resolution because you want to include as much relevant information as you want. However, when you want to simulate the same 2 million computational grid and do and solve fluid flow and transport equation in those grids, it's very difficult because it's very time consuming. Now, if you want to, for example, simulate a reservoir, of course, the area that you want to model is very large. And because of that, you use a large computational grid. The reservoirs are usually very, very heterogeneous. So that means there are huge variations in permeability and porosity. If you have two-phase flow or three-phase flow, of course, because of the capillary pressure and so on, the equations are highly nonlinear. And all of these not only makes computations more difficult and more time-consuming, but also because of the fact that you use a high-resolution computational grid, the time for simulating it dramatically goes up. So, so the question of upscaling is very important. And of course, many excellent people have worked on it. Larry Lake at University of Texas at Austin, Ludo Rossi at Stanford, and many others. They have come up with all sorts of scheme and approaches to address the problem of upscaling. What we did was we did the upscaling by wavelet transformation, and we proposed a new approach based on wavelet transformation. The very first paper published in 1997, its modification was published in 2002. This was for upscaling of single-phase flow, in other words, for upscaling of permeabilities. And then, as I described in a minute, we extended to two-phase flow, to dispersion, to missile displacement, and so on. Okay, so how do we do it? Let's say that we start from the high-resolution geological model. There are a huge number of computational grid blocks in the model. And we fix, of course, the size of the grid by the available data. Okay, so the high resolution data requires high resolution computational grid. The way we upscale it is the following. We upscale based on absolute permeability of each block. So you have a distribution of permeabilities that follow some certain distribution, whatever they follow. Each grid block has its own distribution. We also take into account that around veils in such models, the computational grid must have higher resolution, simply because around veils we have flow disturbances that cannot be taken into account if the computational grid is too coarse. Of course, we can include other things like flow velocities, initial phase saturation, and so on. And we have done it, and we haven't seen any fundamental difference from what I'm going to describe. So what we do is we calculate the wavelet and detail coefficients that I described to you for the permeabilities. So we go to computational grid and calculate this. Each block, let's say in 2 dimensions, each block has 4 wavelet coefficients. 1 is scale, and 3 are details. And remember, the 3 details are x direction, y direction, and diagonal direction. For each of them, we set a threshold. So we have a threshold for a scale coefficient, and we have a threshold for the detail coefficient. And remember, the way we set the scale is that we identify the largest wavelet scale coefficient and the largest detail coefficient, and we normalize all of them by the largest so that they are all between 0 and 1, and then we set a threshold between 0 and 1. 1 for a scale coefficient, 1 for detail coefficient. Now remember, a scale coefficient gave us, I mentioned this earlier, that a scale coefficient gives us information at a fixed scale, whereas detail coefficient gives us information about the contrast between 2 different scales. So what it means is that a scale coefficient at fixed scale gives us information about the importance of permeability at that scale. If the scale coefficient is large, that means the permeability is that block is important. If it is small, that means that block is not important. On the other hand, the contrast is also important, because as you go, for example, from one layer to another layer, or from one large grid block to another grid block, you can have some sort of, because it's heterogeneous, you can have a large contrast. So that is also important. So if the detail coefficient is small, that means that the differences between 2 neighboring blocks is small, so they don't have to be there together. You can merge them into one larger block. Whereas if the detail coefficient is large, that means the contrast between those 2 neighboring blocks is large, and therefore you need to preserve both of them in your computation. All right. So we start doing some of this. If the scale coefficients are larger than their threshold, they stay the same. If the detail coefficients are larger than their threshold, they stay the same. Near the wells, we don't really change anything. We just keep it to be high resolution. All right. So the way to do it for example, wells is that we define a window around wells, and we don't touch it. So let's say, for example, you have a permeability distribution like this that varies between the numbers that you see on the right. It's characterized by a Hertz exponent about 0.3. So that means it's highly heterogeneous. So of course, if you want to do uniform upscaling, then of course you draw different contour lines, and within each you shrink the grid blocks, or you expand the grid blocks. But of course, that's not very really useful, because if you go back to this, some parts have large contrast, some parts have low contrast, and therefore upscaling it uniformly is not wise. So now here, for example, you see, let's say you have 2 wells at 2 corners. Here, for example, you can do it a little bit better by keeping the high resolution around the wells, and then gradually increase it as you move towards the center. However, if you do it with wavelets, then you can see you have the same type of a structure, but now the grid blocks are not uniform everywhere. Where those parts that uniformity is good in terms of the scale and wavelet coefficient, they are large. Those regions where they need to be highly resolved, for example, around wells and areas close to wells, or areas, for example, on top, on the left, next to the wells, where high resolution is needed, the grid blocks are large. All right, so now once you did that, of course, once you start from a very high resolution and then you make these large blocks, so what it means is that you have to calculate the effective permeability of these large blocks based on those small blocks that you had at the beginning. So for example, in this one, in the one at the top, at the bottom, on the left, on the right, you see 4 blocks, small blocks, and then next to it you see a large block. So that large block obviously contains 4 of those small blocks. Each of those small blocks had their own permeabilities, and now in order to replace them with a larger block, you have to calculate the effective permeability of that larger block based on the effective permeability of those small blocks. So that by itself is a problem. You can do it a variety of ways. You can say permeability is Darcy's law is is analogous to Ohm's law. So permeability is not conductivity. So for example, if you have a block consists of 4 smaller blocks, you can use Ohm's law in order to calculate the equivalent electrical or permeability of the block. You can actually solve the flow problem. You can impose a pressure drop across the block and calculate the effective permeability, or you can use the inverse Wavelet transformations, because once you set some of the scale and detail coefficients to 0, and you got this large block, you can inverse the permeability distribution from the Wavelet space into the real space, and that distribution tells you what the permeability would be at larger blocks. So we have used all 3 of them, and we have looked at all of this. We have looked at a pressure transit analysis. It was published in this paper. I won't talk about it. We have looked at unstable miscible displacement, viscous fingering, for example. We have looked at dispersion, which is important in groundwater flow, and we have looked at water flooding. Okay, so let's look at miscible displacement. We know miscible displacement is governed by convective diffusion equation. If you have a fluid flowing in a formation, and then you inject another fluid into the formation in order to displace the in-place fluid, the concentration of injected fluid is C, and that concentration is governed by the mass conservation or convective diffusion equation. So C is the concentration of solute or what you injected, V is the local velocity, and D is the dispersion coefficient. Of course, dispersion coefficients are a function of velocity, and therefore you have to substitute it. Now you can solve this equation numerically, or you can solve it by a random walk. A random walk takes diffusion is equivalent to random walk. So it first takes a diffusive, a convective step, because there's a flow field here, and then you perturb that step because of diffusion. This is well known. It's called particle tracking method. So we solve it by that. We started from a model, 2-dimensional model, that originally had 512 by 512 grid blocks. So something like 265,000 grid blocks was in the original geological model. We know that if the viscosity of the fluid that you inject into the porous medium is much larger than the viscosity of the in-place fluid, then you have unfavorable mobility ratio and you have viscous fingering. That means fingers form that quickly shoots through the system and leave a lot of, for example, oil behind. And that is a very unfavorable situation, but at the same time, simulation of it and upscaling of it is far more difficult. We published this in a paper back in 2004. Here I show you mobility ratio 85. The permeability distribution was generated by a fractional Brownian motion in the Hess exponent of 0.7, and the 2 thresholds, a scale threshold and detailed threshold, were both 0.9. What I show you is pore volume recovered versus pore volume injected. What I injected and what I recovered after the breakthrough. And as you can see, I can hardly say which is which. You know, the triangles are the result of the simulation in the initial high resolution computational grid. The other ones, the circles, are the result of the simulation in the upper scale grid. And as you can see, there is not practically any difference. Most importantly is the breakthrough point, the point at which this curve takes off, because you don't want to predict early breakthrough and you don't want to predict late breakthrough. You want to predict the right breakthrough time, and this clearly gives you the right breakthrough time. Now, on the other hand, if I do this in a very heterogeneous medium with a Hertz exponent of 0.2 and the same threshold and mobility ratio, again, I see very, very little difference between the two curves. So again, upper scaling here works even for very highly unfavorable mobility ratio, which is a viscosity ratio of 85. In other words, the viscosity of the in-place fluid is 85 times larger than the viscosity of the fluid that we injected into the system, and yet we get nice equilibrium. Now, when the viscosities are equal, then we have the problem of dispersion, and we have also looked at that problem by upper scaling in a paper that we published with my colleague at USC, Felipe de Barros, and our student back in Advances in Water Resources in 2016. Now, let's talk about simulation of water flooding. So you have oil in place and you inject water into the system, and you want to upscale this and simulate. We published 3 papers in it, in Transfer Force Media, Computational Geoscience, and Journal of Heat Transfer. So all the details are there. In order to test the method by a very, very difficult problem, what we did was we upscaled the SPE-10 model. SPE-10 model is a model that was set up by Society of Petroleum Engineers, and it's a very difficult model to simulate. It's a 3-dimensional model. The size of the model is 1200 by 2200 by 170 feet. It contains about 1.12 million grid blocks, 60 by 220 by 85. It is part of the branch sequences. Top 70 feet, 35 layers are one formation, and the bottom is another formation. The size of the blocks in the model are 20 by 20 by 2, and there is 8 orders of magnitude difference variation in the permeability. That's huge. 8 orders means 100 million difference. So it goes from 10 to power minus 4 millidarcy to something like 10,000 millidarcy. So that's like 8 orders of magnitude. So it's highly heterogeneous. It is also channelized, which makes it even more difficult. And this is basically a picture of the model. We need, of course, a relative permeability, and we use the standard relative permeability correlations that people use, where S is the saturation, and SWC is a connect water saturation, and SOR is residual oil saturation. The model is anisotropic, and therefore the ratio of the vertical permeability to horizontal permeability is 0.3 for channels and 10 to minus 4 for background. Into the reservoir at 5,000 barrels per day is injected. Maximum hold pressure is 10,000 psi. There are 4 producer wells at 4 corners and 1 injection well. The initial reservoir pressure is 6,000 psi, and the simulation period is 2,000 days. In other words, we want to simulate the behavior of this displacement over something like 5 years or 2,000 days. So that's a long simulation. To simulate for actual 2,000 days, it's very long. Okay, so the governing equation is a standard equation. The pressure equation is given by this, where we have these standard quantities: phase compressibility, rock compressibility, and total compressibility. We have the pressure in the oil phase is governed by this. Q is the injection rate, and so on. Since we generate a computational grid by wavelet that does not have equal size grids, because we don't do uniform upscaling, but we do it with wavelet that generates unequal grid blocks, and then we use finite volume method to solve the governing equation. So in order to do that, we take the equation that I showed you and we integrate both sides over control volume or surface, and use divergence theorem to convert one to the other. These are a standard. To take care of the fact that, for example, you may have a situation like this where four different blocks with four different sizes are neighbor to each other, and therefore when you write the finite volume discrete finite volume equation, you have to take care of the fact that these distances are small and these distances are large, and so on. So when you write this equation, you have to take care of those. It's not all a standard, and you can see it in the original paper. We use adaptive time step because it's not wise to use the same time step everywhere. Let's say, for example, if the front between the two fluids is near the production well, then it is wise to use a smaller time step in order to make sure that we don't move too fast or we don't move too slow. We use formulation which is implicit pressure, explicit saturation, which is called IMPES, is very well known. And we use fully implicit formulation for nearby region and IMPES for the rest of the region. So we do all sorts of tricks in order to make sure that every step of a numerical simulation is done according to the latest state of the art. Okay, these are the details that I already told you about. These are all the details. I don't have to go through it. Okay, so what we did was we obtained the solution of the SP10 models in the original grid, which has 1,122,000 grid blocks on a supercomputer. Okay, and then we use this work. Remember, this work was done long time ago, and this work was done in Iran, not here, not in the United States, because the student that was doing this was in Iran, and therefore he was using the computer Pentium 4 at that time with a speed of 3 gigahertz. So we figured that if we wanted to solve the complete problem with the original SP10 model on his Pentium, it would take 863 CPU days, namely more than 2 years. Okay, but by upscaling it, we reduce the time dramatically. So we generate 5 upscale models with different numbers of number of grid blocks. Remember, the original one had 1,122,000 grid blocks. The upscale one, the 5 ones, one of them had 13,806, the other one had 14,907, and the other 3, 18,522, 21,711, and 21,303 blocks. Okay, and the initial number was 1,122,000. So you can see a drastic reduction in the number of grid blocks from the original SP10 model to the upscale model that we generated. So the question is this drastic reduction, does this drastic reduction preserve the accuracy of the simulation? Because if it distorts the results and the results do not agree the upscale model with the original simulation, then of course it's no good. So the question is, does it do that? So here, for example, the total oil production is shown versus time over 2,000 days. The landmark is that supercomputer. I show 5 results with 22 layers, 24 layers, 30 layers, 36 layers, and 36 layers with injection rate. And you can see all the results, the supercomputer and upscale agree very, very closely, okay, within a very few percent difference. Here, I show the average reservoir pressure. The difference seems large, but actually it's not large, because if you look at the scale of the numbers, you see that the differences are very actually small. But at the same time, average reservoir pressure is not a very well-defined quantity, because you want to calculate the average pressure over the entire reservoir. But the entire reservoir is highly heterogeneous, so the proper average is not very known how you calculate this. But despite that, you will still see pretty good difference. Here, oil production in one of the wells. Here, oil production in another wells. In every case, you see the agreement is actually very good. Here, the difference is a little large, but this is no more than like 8% again. And here, water cut. Again, you see very close to supercomputer calculation. And here, another water cut for well number 3. So what did we get out of this? We got a speed of factor of 5,000. In other words, the initial simulation and the upper scale simulation, the time for them differed by a factor of 5,000. The maximum error in oil production that the upper scale model predicted was only a few percent, 5%, I think, if I remember correctly, at most. Okay, so again, two-phase flow was simulated successfully, upper scale successfully. We have used it for other type of things. For example, we have calculated frequency-dependent conductivity of amorphous semiconductors. This is a very difficult problem. In fact, before we solved it with wavelets, there wasn't good numerical data, and the reason for it is that there is 10 to 15 orders of magnitude variation in the local conductivity. We published it in 2 papers. We have used it for simulating diffusion, flow, reaction in the atmosphere, turbulent flow and diffusion and reaction in the atmosphere for air pollution problem. Again, this is a very difficult problem because the reactions are highly nonlinear, so their kinetics is nonlinear. We have 53 reactants and 117 nonlinear photochemical reactions. This is an extremely difficult problem, especially if you do it for air pollution over a large urban environment, which we did it for the Tehran in Iran, capital of Iran, air pollution problem there. We published it in atmospheric environment. We have also looked at propagation of acoustic and elastic wave in heterogeneous media and analyzed the data with wavelet transformation. We published all of those in several papers. We have looked at it for fractured porous media because upper scaling of fractured porous media is far more difficult than unfractured. And the reason for it is that you have a distribution of fractures. You have large contrast between fractures and metrics and so on. The first step was taken in the paper that we published about a decade ago. So for example, if you have a structure like this is unfractured, this is fractured, and now you can see around the wavelet transformation preserve automatically the fine resolution of the block around the fractures, but then coarsen the rest. But as you can see, the coarsening is not done uniformly, even in areas where there is no fracture, but there are high permeability contrasts, the resolution is preserved. So this is very appropriate upper scaling for a fractured reservoir. Now, finally, the last piece of work that we have done is area which was published a couple of years ago in Transporting Porous Media, and that is when we, in all of this simulation, we always start from regular grids. So, for example, from cubic grids or square grids in 2 dimensions and so on. But in reality, we shouldn't really start from regular grids. We should start from completely irregular grids so that we have flexibility in terms of deciding where the low permeabilities are and where large permeabilities are and so on. Irregular grids also give you the flexibility that you can include the different orientation of the fractures. In the pictures that I showed you, the orientation is either horizontal or at some angle that you see on the right, on the left of the right figure. But with irregular grid, you can have a whole distribution of orientation of fractures. Now, in order to do this, we have to invent a new type of wavelets, because all the wavelets have been invented for regular structure, for regular grids, whereas we wanted to do it for irregular grids. We have done it. We don't have time to go into details, but we published it in Transport in Post Media a couple of years ago. We have also recently used Kerbelet transformation, which is a generalization of wavelet transformation. And wavelet transformations, as I described to you, is used for upper scaling of computational grids. Kerbelet transformation, on the other hand, are used for upper scaling of image of porous media. So nowadays, people have started doing simulation directly in the image of the porous media. They no longer make a cubic grid structure or something like that. They superimpose the grid structure on the image itself and then solve the problem by lattice Boltzmann or a straightforward computational methods. Now, of course, a lot of those details in those images are not useful. They don't do anything other than increasing the computation time. So what we do is we use Kerbelet transformation in order to upscale the images. And the way you do it is you introduce a pair of windows, W and V, and then you define a function U that you see at the bottom of the page, which is defined by in terms of those windows that I'm writing there. And then your Kerbelet transform, or the Fourier transform, or Kerbelet transform, psi hat of I, is basically the same as that function that you built. So what you do is you determine Kerbelet transform of the image, which is defined in a very similar way with wavelet transformation, and then you set the threshold just like wavelets. The advantage of Kerbelet is that, as you can see in this equation, there is orientation, theta. So that means because the image has many different orientation locally, not like a square or cubic structure where the orientation is either horizontal or vertical. Here, any orientation can be taken into account, and therefore you do the same type of thing except that the orientation is taken into account. So we have published 3 papers in it: Geophysical Research Letter in 2020, Transport in Post Media 2021, and Advances in Water Resources in 2021, in which we explain how we upscale images with Kerbelet transformation. And again, I emphasize we do it with Kerbelet because Kerbelet allows you to be very flexible in terms of orientation. So, if I want to summarize my talk in just one or a few sentences, I hope I have convinced you that multi-scale and multi-resolution wavelet and Kerbelet transformation provide accurate, efficient, and unifying approach. I say unifying approach because, as you can see, with one tool, we did a wide variety of problems: denoising the data, analyzing the data, cross-correlation between data, pressure transit analysis, miscible displacement, immiscible displacement, dispersion, and so on. So it provides a unifying approach to all these problems with just one toolbox, and that is wavelet or Kerbelet transformation for solving problems in porous media and modeling multiphase transport and fluid flow in them. There is also a little advertisement here. I have a book that published on flow and transport in porous media. It is in its 2nd edition. This is a picture of the 1st edition, but it's 2nd edition. So this is a free commercial that I take advantage of here. I'll be happy to answer any questions that you may have, and I thank you for paying attention to my talk.
Thank you very much. Mohammed, for your nice presentation, your nice talk. You
Thank you.
cover a lot of things that you say on the on your last slide.
Yes.
So now we are open to questions. So please use the chat to write your questions, and we can do the questions for Mohammed. We have a comment of that now we are putting the comments on the screen so you can see it. So uh, in general, I guess people are saying that you show us a lot of things very interesting, a lot to read and learn, and a quite range of application of the wavelets for some fractured media.
Thank you.
So,
By the way, one thing I wanted to mention is that if this type of work is of interest to any of you that are listening to this talk and are interested in collaborating with me, I'll be more than happy to collaborate, establish a program collaboration and work together. If you want, for example, to send your student to a USC for a period of 6 to 1 year to work with me to learn these things, I'll be more than happy to host students to come to USC and work with me. So there are all sorts of possibilities for collaboration and working together, which I'll be happy to do.
thank you very much, Mohammed. For sure, we have some students interested on working on this kind of thing, and I guess these topics of formation factor F and the way you can see the discontinuities on the
Yes.
media.
Mm-hmm.
That's to see the failure parts of soils and different materials, for example.
Yes. Yes.
Yes, yes, that's very nice. I don't see any questions on the chat. We get. I was monitoring the activity on the YouTube site, and we have 20 assistants to your conference. So thank you very much for your nice talk.
Thank you very much, and I hope to see you at some point in the future.
Yes, of course, for sure. We have to talk more to do these exchanges of our students to work with you in very interesting things. So I'm waiting for one or more or two questions.
So if there is no question,
I have one here.
yes, of course.
I'm going to read. So you say, on a regional scale, the method of scaling of permeability by multiscale wavelet transformation in heterogeneous media has shown good results, as you summarize in the paper you published in 2009. The question is, in countries like Colombia, where the hydrogeological development is incipient and we have a lot of scarcity of information, is much greater than in another latitudes. Does it see promise to implement this technique in academic studies aimed at characterizing heterogeneous media? What do you think about that if you have scarcity of information to apply your models?
I believe it would work. I have actually thought about it. I haven't done it, but based on what I know about such formation, it should work because uh, we have tried it for various types of formation. We have tried it for carbonates. We have tried it for sandstone. We have tried it for medium that have strong discontinuities like fault and fracture. Um, so if I were to guess, because I haven't done it, I would say it should work just as well, based on the experience that I have. But of course, we don't know it unless we actually do it.
So that's a good question. In our country, we have a lot of developments in oil and gas industry, but the information is maybe scarce or located only on the reservoirs, the oil and gas reservoirs, and not on the other formations. So that the thing, one of the things is how we can use whole information that we have, at least, to characterize the rest of the formations. That's
Well, I mean, you have to analyze the data that you have, and then you have to use a stochastic modeling, because there are large regions where you don't have any information, and therefore you have large uncertainties. So the only way to take into account the effect of large uncertainty is to generate a stochastic realization of the medium, where in some parts of it, a limited area, you may have some information, and in other areas you don't have any information. So a stochastic modeling is the way to go. If you have, for example, an image of a small portion of it, then that image can be reconstructed based on some geostatistical modeling that I've been working over the past few years. And then once you do that, once you construct it, in other words, you make a model for the image that you have, then you can extend it to larger extent. And since this reconstruction is stochastic, that means that you can generate many realizations of it, and therefore it gives you a view of the order of magnitude of the uncertainty, what type of uncertainty you have. In reservoir modeling, as you know, we always have great uncertainty because the data are limited, and therefore a stochastic simulation is the best way to go, because it gives us a way of getting a handle on those uncertainties. In the old times, people would use things like kriging, for example. But kriging is deterministic and cannot give any information about the uncertainty. So people now use a stochastic modeling, and that can be done.
Thank you very much for your answer. So we don't have any more questions. So finally, I want to express the acknowledge to Interport, the International Society for Porous Media, and to Kimberly-Clark, this famous company who sponsor this talk. We wish you were here for this talk, but unfortunately these COVID things doesn't let you come to Colombia to visit that. But you are also invited here to come whenever you want. We need to explore the opportunities to invite you to come to see you, to work with our students, giving your talks. It will be a pleasure for us.
I'll be more than happy to visit. If there is an opportunity, I'll be more than happy to come, and I can give a series of lectures about the work I have done. We can talk about collaboration. We can talk to students. I'll be more than happy. It will be my honor and pleasure to come.
Okay, this is the end of this talk. Thank you very much. We are to finish the YouTube live with the final video of our school Andres, please. Again, thank you very much, Mohammed. See you on the
Thank
next
you very much and have a good day, everybody.
Universidad Nacional de Colombia, proyecto cultural, científico y colectivo de Nación.